Exercise 17a, the derivative. We estimated the instantaneous rate of change by doing the smallest, tiniest little line that we possibly can. Do you remember that? That was from chapter 16d, if I remember correctly, where we just tried to get the smallest line we could, or we used a tangent line, but we tried to get the smallest line we could to be able to estimate the instantaneous rate of change at a particular point, because we can't just use one set of coordinates to estimate an instantaneous rate of change. We need two. That's the definition of gradient, y2 minus y1. You can't have y2 without a y1, that kind of thing. So we're going to estimate the instantaneous rate of change for when y equals for the graph y equals x squared, when x is equal to 1. So when x equals to 1, we want to find the instantaneous rate of change, which in this topic we call the derivative. So if you hear me say the word derivative, that is shorthand for saying instantaneous rate of change. So we'll make a little line between, say, 1 and 1.1. As you can see here, I found my values, and what I'm doing is I'm just going to find the gradient of that. So if I do my y2 minus y1 over x2 minus x1, so I'll get 1.21 take away 1 over 1.1 take away 1, then I get an answer of 2.1, which we've identified here. But what if I made that line even smaller? So I've got 1 and 1, and I got 1.01 and 1.0201. So again, y2 minus y1 over x2 minus x1. And that gets me 1.0201 take away 1 over 1.01 take away 1. I feel like I start sounding like a machine. 1, 1, 1, 1, 1, 0, 0, 1, 1, 1. Well, this is equal to 2.01, which we've identified here. So, when we did this estimate, the gradient was equal to, or the instantaneous rate of change was equal to 2.1. When we went this close, the instantaneous rate of change was 2.01. Does that mean that we could say that the derivative at x equals 1 is 2? Possibly. Very, very possibly. But in order to do that, we need a very, very tiny line. A line so small that it actually doesn't exist. In all of these examples, we have made very tiny lines. That's the best way to, because we need the y2 and minus the y1. However, to be able to really discern what the instantaneous rate of change is, basically I just want to know what it is at that point and no other point. But I can't do that. I can't do that without another coordinate. So this is when, fair viewers and subscribers, what we need to do is do a wonderful case of what I would like to rather unflatteringly call bullcrap mathematics. We're going to have to invent a distance that doesn't exist. So what we're going to do to find out what the genuine instantaneous rate of change is, we're going to make a line so small, so infinitesimally small, that it could be mistaken for a 0, but it can't be 0. It can't have a line that's 0 long. We'd have a 0 length line. That's ridiculous. That would be silly. It would be cast out. But what if we could? What if we could make a line that was actually 0 long? Well, we can't use 0 because people will, it catches out and the jig will be up. So what we're going to do is we're going to use the letter H. This H represents the tiniest possible distance that I could possibly do. And then you think, all right, well, if I can't make H equal to 0, what can I do? I want to make that distance. As you can see here, I've got 1 and 1 plus H. So that just means it's a little H distance away. And so therefore I just substituted that into, so subbed 1 plus h into y equals x squared. So I just made that 1 plus h a little bit away. I want to make that h 0, but I can't make it 0, otherwise that'd be silly. I need a second point. So what if I was to make the limit as h approaches 0. And now we have a practical application for that limit topic. I'm going to make the limit of h approach 0, but not actually 0 because that will cancel everything out. But I can actually make it equal or as close to 0 as humanly possibly can. So what I'm going to do is I'm going to state, I'll get my instantaneous rate of change, which we call the derivative. And we're going to do y2 minus y1 over x2 minus x1. So here I'm going to call that x1, y1, x2, y2. So I'm going to do 1 plus h squared minus 1 over 1 plus h minus 1. And so then I just need to expand that top line, 1 squared plus 2h plus h squared minus 1. 1 plus h, take away 1, it will just leave me an h. And so 1 squared is 1, take away 1, 0, 2h plus h squared over h. And then what we're going to do is we're going to simplify. And we'll take those h's out, given that h does not equal 0, making sure that we don't say that. And then we get 2 plus h. So now the limit as h approaches 0, we get 2 plus 0, which is equal to 2. So what is all of this calculated? This is calculated. If I was to make that little line, just an h distance, a tiny distance, an infinitesimally small distance, and I make that distance shrink closer and closer to 0, without saying 0, because it's not, can't do 0, can't do a line that's 0 long, but as close to 0 as possible, then I have found that the instantaneous rate of change when x equals 1 is indeed equal to 2. And thus, we have found the basis of all things calculus. We have been able to go and do a thing called a derivative. Just some handy, and what this is an example of, this is an example of doing a derivative by first principles. So if you ever see first principles, it means you have to do it this long way. So we have found the instantaneous rate of change when x equals 1. Hooray, go us. But does that mean we have to do the same laborious process for every other value of x? What about if I had a question which told me I need to find the instantaneous rates of change at 1, 7, 2053, whatever? I'm going to have to do a lot of substituting. Well, what we can actually do is make a little formula that will help us create or generate any instantaneous rate of change that we want. And that's when we have the derivative formula. The derivative formula, which if we use f of x notation, it's f apostrophe x here, f apostrophe brackets x equals the limit as h approaches 0, fx plus h. So that's just, all that means is I've just substituted x plus h into the equation, minus the original equation, just with all the x's in there, all over h. Now, if your equation doesn't have an f of x, and it just says y equals like this, then we use this notation, dy dx. So, and what does that mean? It means the change in y with respect to the change in x, which you might remember when we used this terminology when we were calculating gradients in the previous chapter. Example 2, let f of x equals x squared minus 3x. Then the points P, 4, 4, and Q, 4 plus h squared minus 3, brackets 4 plus h, close brackets, are on the curve y equals f of x. A, find the gradient of the secant PQ. What does a secant mean? It just means a line segment. And we'll find the gradient of the tangent line to the curve at the point P by considering what happens as h approaches 0. The gradient of the tangent line to the point P. If you see this phrase, tangent line Find the gradient of the tangent line to the point. So that's if I've got a big old curve, got a tangent line, and they just touches one point. The gradient of the point that it touches is equal to the gradient of the line. This little relationship will help you quite a lot in methods, as long as you remember that the gradient of the tangent line is the same as the gradient at the point at which it touches. So let's start with A. We're going to find the gradient of the secant PQ. So I'm going to do x1 is equal to 4, x2 is equal to 4 plus h, y1 is equal to 4, y2 is equal to 4 plus h squared minus 3 plus 4 plus h. A lot of people get very confused when reading this coordinate because it's so much spaces and minuses and things like that. Just remember that everything after that comma, that is y2, and then this is x2. So just remember that, because that is where a lot of people trip up. They misread those coordinates. So now I'm not a fan of now, as much as I do like to have factorized things, doing this, however, is best done when everything is not factorized. So I'm just going to put 16 plus 8h plus h squared minus 12 plus, oh no, that's going to be a minus 3h. So that's going to be 4 plus a 5h, yes, 5h plus h squared. So now we can do the gradients. The gradient y2 minus y1 over x2 minus x1. So then for part B, we need to find the gradient of the tangent line, that point P. So all that means there is that the limit as h approaches 0 will be 5 plus 0, which is equal to 5. So that is the gradient of that tangent line. Example 3, find the limit as h approaches 0, this nonsense. So one of the things that is very helpful to know if you're doing something wrong is that if you get to this step in any of the calculations that we do and everything in the top row has an h in it, then you know you're fine. And that bit of wisdom may not make sense until we do another one of these examples. But essentially all I'm going to do here is just take a common factor of h out. So the limit as h approaches 0 is 3x squared minus 2x 0 plus 1, which is equal to 3x plus 1. Example 4, find the derivative for 2x cubed plus 7. So this will take a little bit of work, but that's okay. We're going to get an x1. So this is not asked for this is just finding the derivative for this. Now what this is saying, you'll notice that it doesn't say when x equals 4, it doesn't say when x equals 1, it's just finding the derivative. So what this is saying is make a formula for any value of x. So that means what I want to do is I want to generate a formula that if I was to put any value of x into it, then that will make the derivative, or that would find I could calculate the specific instantaneous gradient at any of those points. So I'm going to label, to do this, what we need to do is we need to label x1 and y1. So x1 will just be x because we want it for any x. We want to do it, you might remember it's that example of that tiny picture. Remember how we were doing the 1 and the 1 plus h? Well, instead of 1 and 1 plus h, we're going to do x and then x plus h. So I'm just going to substitute x into the original equation, which is be 2x cubed plus 7. And then x2 is equal to x plus h. We just want a tiny distance away. y2 is equal to 2 brackets x plus h cubed plus 7. Again, I would, as much as this is a pain to expand a cubic bracket like this, it is worthwhile in the long run. I never remember what the cubic bracket expansion is, so I do my expansion the chump way. Now let's do the first principles from the very beginning. So we're going to do y2 minus y1, x2 minus x1. Congratulations for those who can use binomial theorem to do all that lovely expansion, or just happen to memorize these. Now I'm going to write this down. I'm just doing the y2. There's y2. I'm going to minus. Now I had a student ask me about why I put this in brackets. And it's because everything in y1 has to be subtracted. Everything does. So this reminds me that I will need to minus literally everything, the 2x cubed and minus the 7. If you have to do this by first principles, which you are expected to do, and you get to this step and you've got, I don't know, a number left over, or some sort of number, or an x that doesn't have an h in it, you have done something wrong and you need to go back and check. There should just be h's all over the numerator here. So now we have made a formula that if I substituted x for any number, I could find the instantaneous rate of change at that point. I'm going to leave you with this small question. That was the question that we were asked, and this is the answer. Can you see if there is any pattern between the question and the answer? Have a look. Is there any way that I could just look at the question and generate that answer?